Quantum entanglement is one of the most bizarre and counterintuitive concepts in quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels. It describes a strange connection between two or more particles, where they become linked in such a way that they share the same fate, no matter how far apart they are. Imagine two particles, born together in a single event that fly off in opposite directions at nearly the speed of light. According to quantum mechanics, these particles can become entangled, meaning that their properties, such as their spin or polarization, are correlated even when separated by vast distances. This means that if we measure the spin of one particle and find it to be spinning clockwise, we instantly know that the other particle, no matter how far away it is, must be spinning counterclockwise. This connection between the two particles is instantaneous, meaning that it happens faster than the speed of light. This spooky action at a distance, as Einstein famously called it, has puzzled scientists and philosophers for decades, as it seems to violate the fundamental principle of locality, which states that objects can only be influenced by their immediate surroundings. The implications of quantum entanglement are profound, as it challenges our classical understanding of the universe and suggests that there is a deeper, more interconnected reality beneath the surface of our everyday experience. It also has the potential to revolutionize many fields, including computing, cryptography, and teleportation. In the following sections, we will delve deeper into the mysteries of quantum entanglement, exploring its properties, implications, and potential applications. To understand quantum entanglement, we need to first grasp the concept of superposition. In the quantum world, particles can exist in multiple states simultaneously. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, an electron can be in a superposition of spin-up and spin-down states. It's not until we measure its spin that it collapses into one definite state. Now, imagine two coins flipping in perfect synchronization, their states intertwined. If one lands on heads, the other instantly lands on tails, no matter how far apart they are. This is analogous to entangled particles. When two particles become entangled, they are no longer independent entities but rather exist in a shared state of superposition. This shared state persists even when the particles are separated by vast distances. This interconnectedness is what makes entanglement so bizarre. If we measure the state of one entangled particle, we instantly influence the state of the other, regardless of the distance between them. This instantaneous influence doesn't involve any physical signal traveling between the particles. It's as if they are connected by an invisible thread, allowing them to communicate instantaneously. This spooky action at a distance is one of the most perplexing aspects of quantum mechanics, and has been the subject of much debate and experimentation. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper that highlighted what they believed to be a flaw in quantum mechanics. This paper, known as the EPR paradox, argued that the theory's prediction of instantaneous action at a distance was incompatible with the principle of locality, which states that an object can only be influenced by its immediate surroundings. The EPR paradox presented a thought experiment involving two entangled particles that are separated by a large distance. According to quantum mechanics, measuring the state of one particle would instantly determine the state of the other particle, even though they are too far apart for any signal to travel between them at the speed of light. Einstein and his colleagues argued that this violated the principle of locality and suggested that quantum mechanics was incomplete. They proposed that there must be some hidden variables yet to be discovered that determined the properties of each particle before measurement, and that these hidden variables were responsible for the apparent spooky action at a distance. However, subsequent experiments have consistently confirmed the predictions of quantum mechanics, demonstrating that the correlations between entangled particles are stronger than any classical theory, including hidden variables, can explain. The EPR paradox, while initially intended to expose a weakness in quantum mechanics, ultimately served to highlight the theory's profound strangeness and its departure from our classical intuitions about the nature of reality. It forced physicists to confront the implications of entanglement, and to grapple with the possibility that the universe might be fundamentally non-local. This debate continues to this day, prompting new experiments and theoretical frameworks that seek to reconcile quantum mechanics with our understanding of space, time, and causality. The term spooky action at a distance was coined by Einstein to express his discomfort with the non-local nature of quantum entanglement. He found it unsettling that the state of one particle could be instantaneously affected by the measurement of another particle regardless of the distance between them. This seemed to suggest that information could travel faster than the speed of light, violating a fundamental tenet of Einstein's own theory of relativity. However, it's important to note that while entanglement does involve a kind of instant correlation between particles, it doesn't allow for the transmission of information faster than light. The act of measuring one entangled particle doesn't allow us to send a message to the other particle. The correlation between their states is pre-established at the moment of entanglement and cannot be used to communicate information. Imagine two people, Alice and Bob, each receiving one of a pair of entangled gloves, one right-handed and one left-handed. If Alice opens her box and finds a right-handed glove, she instantly knows that Bob has the left-handed glove, and vice versa. However, this knowledge doesn't allow Alice to send a message to Bob faster than light. The correlation between the gloves was pre-established when they were packaged together, and Alice's discovery of her glove doesn't change the fact that Bob already has the other glove. Quantum entanglement is also closely linked to the measurement problem in quantum mechanics. The measurement problem arises from the fact that particles in quantum mechanics exist in a superposition of states until they are measured. Upon measurement, the superposition collapses, and the particle assumes a definite state. This collapse of the wave function, as it's known, is a discontinuous and seemingly random process that has puzzled physicists for decades. Entanglement adds another layer of complexity to the measurement problem. When two entangled particles are measured, their wave functions collapse simultaneously, even if they are separated by a large distance. This raises the question of what constitutes a measurement, and how the collapse of the wave function is transmitted instantaneously between entangled particles. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that the act of measurement itself causes the wave function to collapse. Others, like the many worlds interpretation, propose that all possible outcomes of a measurement actually occur, each branching off into a separate universe. Entanglement further complicates these interpretations, as it implies a non-local connection between particles that seems to transcend the boundaries of space and time. Despite its mind-bending nature, quantum entanglement is not just a theoretical curiosity. It has the potential to revolutionize various fields, from computing and cryptography to teleportation and imaging. As our understanding of entanglement deepens, we are discovering innovative ways to harness its power for practical applications. One of the most promising applications of entanglement is in the field of quantum computing. Quantum computers leverage the principles of superposition and entanglement to perform calculations that are impossible for classical computers to solve efficiently. This has the potential to revolutionize fields like drug discovery, materials science, and artificial intelligence. Another area where entanglement shows great promise is in quantum cryptography. Traditional cryptographic methods rely on the difficulty of factoring large numbers, a task that is challenging for classical computers but could be easily solved by quantum computers. Quantum cryptography exploits the principles of entanglement to create unbreakable encryption keys, ensuring secure communication even in the face of quantum computing threats. Quantum computing harnesses the principles of quantum mechanics to perform computations in ways that classical computers cannot. It leverages the concepts of superposition and entanglement to store and process information in quantum bits, or qubits. Unlike classical bits, which can only be 0 or 1, qubits can exist in a superposition of both states simultaneously, allowing quantum computers to store and process vastly more information than their classical counterparts. Entanglement plays a crucial role in quantum computing by enabling qubits to be linked together in a way that allows them to influence each other's states instantaneously, regardless of distance. This interconnectedness enables quantum computers to perform computations on multiple values simultaneously, leading to exponential speedups for certain types of problems. Imagine searching through a maze. A classical computer would have to explore each path sequentially. In contrast, a quantum computer could explore all paths simultaneously, finding the solution much faster. This ability to perform parallel computations makes quantum computers well-suited for tackling complex problems in fields like drug discovery, materials science, and optimization, where the number of possibilities explodes exponentially. While still in its early stages of development, quantum computing holds the potential to revolutionize scientific research and technological innovation. Quantum cryptography leverages the principles of quantum mechanics to create unbreakable encryption keys, ensuring secure communication. Traditional cryptographic methods rely on the difficulty of factoring large numbers, a task that is challenging for classical computers, but could be easily solved by quantum computers. This poses a significant threat to current encryption methods, as the advent of powerful quantum computers could render sensitive data vulnerable to attacks. Quantum cryptography addresses this threat by using entangled particles to generate encryption keys that are provably secure. One popular method, known as quantum key distribution, QKD, involves sending entangled photons through a fiber optic cable. Any attempt to intercept and measure the photons would disturb their entangled state, alerting the legitimate users to the presence of an eavesdropper. This ensures that only the intended recipients have access to the shared encryption key, making communication virtually unhackable. The use of entangled particles for key distribution guarantees the security of the communication channel, as any attempt to eavesdrop on the key exchange will inevitably leave detectable traces. This makes quantum cryptography particularly appealing for applications where data security is paramount, such as government communications, financial transactions, and healthcare records. As quantum computers continue to advance, quantum cryptography is becoming increasingly vital for safeguarding sensitive information in the digital age. Quantum entanglement, once a perplexing theoretical concept, has emerged as a powerful tool with the potential to revolutionize various fields. From quantum computing and cryptography to teleportation and imaging, the applications of entanglement are vast and rapidly expanding. As our understanding of this bizarre phenomenon deepens, we can expect even more innovative and transformative applications to emerge. One exciting avenue of exploration is the development of quantum networks, where entangled particles could be used to connect distant quantum computers, enabling distributed quantum computing and secure communication on a global scale. Entanglement also holds promise for advancing our understanding of fundamental physics, shedding light on the nature of space, time, and gravity. Despite its remarkable potential, quantum entanglement remains a challenging field with many open questions. Further research is needed to develop practical and scalable technologies that can fully harness the power of entanglement. However, the rapid pace of progress in recent years suggests that we are on the cusp of a new era, where the strange and counterintuitive world of quantum mechanics will shape the future of technology and our understanding of the universe.